Welcome to this scientific lecture on how artificial intelligence is revolutionizing flavor creation by navigating the complex chemistry of aroma molecules. Flavor perception emerges from a high-dimensional chemical space where volatile organic molecules interact with our sensory receptors. Let's begin by understanding the fundamental chemistry underlying flavor perception. Volatile organic compounds typically contain carbon, oxygen, hydrogen, and nitrogen atoms arranged in specific three-dimensional configurations that determine their sensory properties. The volatility of a molecule, which determines whether it reaches our olfactory receptors, depends inversely on molecular weight and exponentially on the enthalpy of vaporization divided by thermal energy. This plot shows the exponential decay of volatility with increasing molecular weight, explaining why small molecules dominate our flavor experience. A key question in flavor science is, what molecular features cause different compounds to produce similar odor perceptions? Functional groups like alcohols, aldehydes, and carboxylic acids create characteristic odor families through their electronic properties and hydrogen bonding capabilities. To enable AI-driven flavor discovery, we must represent molecules as mathematical vectors capturing their chemical properties. Machine learning models encode molecular structure, physicochemical properties, and three-dimensional shape into high-dimensional feature vectors. A typical molecular fingerprint includes molecular weight, lipophilicity log P, hydrogen bond donors and acceptors, plus extended connectivity fingerprints that encode substructure patterns. Modern molecular representations span 200 to 2,000 dimensions, capturing the rich chemical space necessary for accurate property prediction. Principal component analysis projects this high-dimensional space into two dimensions, revealing clusters of molecules with similar chemical features. How does molecular chemistry translate into the subjective experience of flavor in the human brain? Odorant molecules bind to olfactory receptors in the nasal epithelium, generating neural signals that the brain interprets as specific odor perceptions. The binding affinity between molecule and receptor follows thermodynamic principles, with dissociation constant Kd determining activation strength. Humans possess roughly 400 functional olfactory receptor types, each responding to different molecular features with varying sensitivities. Each molecule activates a unique combinatorial pattern across receptor types, creating a neural barcode that the brain decodes as a specific smell. The critical insight is that molecules activating similar receptor patterns tend to produce similar odor perceptions, even if chemically distinct. To train predictive models, we need large datasets mapping molecular structure to human flavor perception. Flavor databases contain thousands of compounds with sensory descriptors obtained from trained panels and gas chromatography olfactometry experiments. Current flavor databases contain roughly 1,000 to 10,000 characterized compounds, each with multiple sensory descriptors. Each compound is typically described by 5 to 20 flavor attributes like fruity, floral, green, sweet, each rated on intensity scales. Here we see a heat map representation, showing how a single molecule scores across 8 different flavor dimensions with varying intensities. A major challenge is that perceptual data is inherently sparse, noisy, and varies across individuals due to genetic and cultural factors. What machine learning architecture can best map molecular structure to flavor perception? Deep neural networks with multiple hidden layers learn nonlinear mappings from molecular fingerprints to flavor descriptor vectors. The neural network function maps molecular input vector X to flavor output vector Y, parameterized by learnable weights theta. Training minimizes the mean-squared error loss between predicted and true flavor vectors across all N training examples. A typical architecture uses progressively smaller layers, like 1024, 512, 256, and 128 hidden units, compressing molecular information into flavor space. Training curves show model performance improving with epochs, with training and validation R-squared converging around 0.75 to 0.85, indicating reasonable predictive accuracy. To propose novel flavor pairings, we need rigorous metrics for molecular similarity. The Tanimoto coefficient measures molecular similarity as the ratio of shared substructures in the intersection to total substructures in the union. This Venn diagram illustrates two molecules as sets of chemical features, with shared features in the overlap and unique features in non-overlapping regions. Euclidean distance and feature space provides an alternative similarity metric, measuring straight-line distance between molecular descriptors. An important question is which similarity metric best predicts perceived flavor similarity between molecules. Empirical data shows moderate positive correlation between molecular similarity and flavor similarity, with correlation coefficients around 0.6 to 0.7. The answer is that learned embeddings from neural networks typically outperform classical similarity metrics by capturing nonlinear flavor-relevant features. The flavor pairing hypothesis suggests that ingredients sharing key volatile compounds create harmonious combinations. Two foods sharing a key volatile compound are hypothesized to pair well because they activate overlapping sensory pathways. A classic example is strawberry and basil, which both contain methyl cinnamon, creating a fruity floral bridge between the ingredients. We can quantify pairing potential as a weighted sum of Tanimoto similarities across all shared volatile compounds, with weights reflecting perceptual importance. The global flavor network represents foods as nodes and shared compounds as edges, revealing clusters of ingredients with high pairing potential. How can AI systematically discover novel flavor pairings from molecular databases? The computational pipeline takes molecular databases as input, applies trained models to compute similarity scores, and outputs ranked pairing candidates. For a database of n molecules, the number of possible pairwise comparisons grows quadratically as n choose 2 equal to n times n minus 1 divided by 2. A back-of-envelope calculation. 10,000 molecules yields approximately 50 million possible pairings to evaluate. This quadratic scaling means computational cost grows rapidly with database size, requiring efficient algorithms for large-scale screening. The solution is to use clustering algorithms and approximate nearest neighbor methods to reduce the search space while maintaining discovery quality. Let's examine specific examples of AI-discovered flavor pairings that chefs have validated. Caviar and white chocolate share trimethylamine and several fatty acid derivatives, creating an unexpected umami-sweet pairing discovered by AI and confirmed delicious by chefs. The Tanimoto similarity between caviar and white chocolate volatile profiles is 0.23, suggesting moderate molecular overlap. Pear and gorgonzola share esters and terpenes, creating a sweet umami combination that AI predicts and chefs validate as a harmonious pairing. The Tanimoto similarity between pear and gorgonzola is 0.31, indicating a slightly higher molecular overlap than caviar and white chocolate.